Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are going to help the students who are preparing for CSIR NET, GATE, NT exam, PhD exam, SET exam, TIFR, uh, JEST, and IIT JAM, and other exams related to physics. So, guys, and also I would thank you everyone who have subscribed my channel, and also I would request the people who haven't subscribed my channel yet, please subscribe my channel. Today I'm going to solve quantum mechanics PYQ. It is a lecture number 2. Okay, so I'm going to start now. I'll start with question number 1. Okay, so question number 1 is, in a system in a system consisting of consisting of two spin half particle two spin two spin half particles labeled labeled 1 2 1 and 2. Let vector s1 equal to h cut by 2 sigma 1 and vector s2 equal to h cut by 2 sigma 2. denote the denote the corresponding spin operators corresponding spin operator spin operators. Here sigma equal to sigma x, sigma y, sigma z, and sigma x, sigma y, sigma z are sigma x, sigma y, sigma z are the three Pauli matrices, the three poly, 3 poly matrices. In the standard basis, in the standard basis, the matrices for the operators for the operators Sx1 Sx1 into Sx Sy2 and Sx2 are respectively are respectively options are given. Option number A, h cut square by 4 0 1 sorry 1 0 0 minus 1 comma h cut square by 4 minus 1 0 0 1. Option B is h cut square upon 4 cut square upon 4 I 0 I 0 0 minus I 0 minus I comma h cut square upon 4 minus I 0 minus I 0 0 I 0 I and option C is h cut square upon 4 0 0 0 0 0 minus I 0 I 0 0 minus I 0 minus I 0 0 0 0 I 0 0 comma h cut square upon 4 0 0 0 0 0 minus I 0 0 minus I 0 0 minus I 0 0 I 0 0 0 I00 and I00 I00 I000. Okay, and option D is h cut square upon 4 0100 0100 1000 000 minus I and 00 comma h cut square upon 4. This is 0 minus I, 0 minus I, 00 iota 000 0001 0010. Okay, so these are the options which are given. We'll solve it now. Okay, just give me 1 minute. Actually, there is some technical error. I'm just checking this for you. Just give me 1 second. 1 minute. I'm just sorting it out. Okay, I apologize for inconvenience. Actually, there was some technical error and I rectified that. Okay, so now we are going to continue. Okay, so the question is, question in a system consisting of two spin half particles. So two spin half particles are given. There is a system of two spin half particles labeled 1 and 2, and let S1 equal to h cut by 2 sigma 1 and S2 equal to h cut by 2 sigma 2 denote the corresponding spin operators. Here sigma, which is sigma x, sigma y, sigma z, or we can say sigma 1, sigma 2, sigma 3, are three Pauli matrices in standard basis matrices for the operators. Uh, the matrix in the standard basis, the matrices for the operator Sx1, Sxy, and Sy1, Sx2 we need to find out. Okay, and options are given. We are going to solve it. Okay, so we'll write here. This is Sx Sx1 into Sy Sy1 Sy2 Sy2. Okay, so we know the value is given, right? This is h cut by 2 sigma sigma 2 s2 and s1. These are spin operator. Okay, h cut by 2 sigma 1, right? So here this is going to be h cut by 2 sigma, that is sigma 1. Sigma 1 we know, right? Pauli matrices. I'll write it for you as well. Pauli matrices sigma 1 equal to sigma x equal to 0 1 1 0. Okay, sigma 2 equal to sigma y equal to 0 minus iota and iota 0. Okay, and sigma 3 equal to sigma z equal to 1 0 0 minus 1. Okay, so these are the Pauli matrices. So here this is sigma 1 sigma 1. So we'll write the value of sigma 1. So it is going to be 0 1 1 0, and we'll multiply this with sy2, that is again h cut by 2 will multiply here, so it is going to be h cut square upon 4, or it is and going to be 0 minus iota iota 0. So now we'll solve it. So in standard basis you can solve like this. Okay, h cut square upon 4 will multiply 0 with this multiply 0 with this complete matrix, then 1 with this complete, and then 1 with this complete, and 0 with this. So this is going to be 0 0 0 0 0. We have multiplied 0 with complete matrix, and now 1. So 0 minus iota 0. So we have multiplied 1 with this complete matrix. So if we multiply by 1, it will remain same. 1 0 0 1 iota minus iota, and 0 1 iota iota, and 1 0 0. Okay, similarly we'll multiply by this 1, so it is going to be 0 minus iota, iota 0, and this is going to be 0, 0. Okay, now we'll now we'll solve s2y, sy2, sy2 sy2 into sx1, so it is again h cut square upon 4, and then we'll write the value. So this is s2y 0 minus iota, so sigma 2, right, and iota 0 into sigma 1 is going to be 0 1 1 0. We'll multiply it, so it is going to be h cut square, it is again going to be 0 0 0 0, and this is going to be 0 minus iota, iota 0, iota 0, and 0 0 0 0. Okay, this is okay. So this is the matrices for these two operators. So the correct option is, which option is matching? Option number C is matching, right? H cut square upon 4, so these two values, h cut square upon 4 in these two matrices. Okay, so this is done. So it has a second part as well, so we are going to solve that second part also. These two operators, it is talking about these two operators. Okay, these two operators, satisfy the relation, satisfy the relation satisfy the relation number A, sx1 spin operator. Okay, vector, I'm not writing this vector because it is getting complicated then. So sy2 comma sy1 into sx2. Okay, this is anti-commutation. Option B is anti-commutation, sx1 into sy2 comma sy1 into sx2. Okay, option C is sx1, this is commutator. Okay, sx1 sy2 comma sy1 sx2. x2 equal to this is equal to 0. Okay, this is equal to iota sz1 and Hz2. Okay, and option D is commutation Sx1, Sy2 into 1 into Sy1 into Sx2 equal to 0, and this value is Sz1 and Sz2. Okay, these are the options given. Okay, these two operators satisfy the relation. So for this, the correct option is this option D, and these two operators commutate, right, with Sy1 and Sx2 equal to 0. Their commutation is 0. Okay, so so now we're going to solve question number 2. Question 2. Okay, so there is some technical error I'm getting today. I hope it will get rectified. Okay, still I'm continuing the class. Okay, so next question is the energy of the first excited quantum state. The energy of the first excited energy of the first excited quantum state quantum state quantum state of a particle of a in two-dimensional potential in the two-dimensional potential Vxy Vxy equal to half m omega square half m omega square into x square plus 4y square. Okay, is options are option number A 2h cut omega, option B 3h cut omega, option C 3 by 2 h cut omega, 3 by 2 h cut omega, and option D is 5 by 2 h cut omega. 5 by 2 h cut omega. Okay, so the energy of the first excited quantum state of the particle in the two-dimensional potential, that's what we need to find. Okay, so we are going to solve it. Since we have been given the potential, that is Vxy equal to 1 by 2 m omega square x square plus 4 y square. So we can write this as 1 by 2 1 by 2 m omega square x square plus 1 by 2 m 2 omega whole square y square, we can write it. Okay, so now we can we know the energy for energy eigenvalue for this is going to be nx plus half h cut omega, because this is in the form this. Okay, and ny plus half 2 h cut omega. Okay, this is going to be the energy. So we need to find out first excited state. For ground state, for ground state, energy E0 is going to be uh, ground state nx equal to ny is going to be 0. Okay, so it is going to be 0 plus half h cut omega plus 0 plus half 2 h cut omega. Okay, so ground state energy is going to be half h cut omega plus h cut omega, right? 2 will get cancelled. Okay, so it is going to be 3 by 2 h cut omega, but we need to find the energy of the first excited state. So first excited state energy is going to be E0 equal to nx, E1 equal to nx plus half h cut omega plus ny plus half 2 h cut omega. So here for first excited state, nx is going to be 1 or ny is going to be 0, right? So we take minimum value. If we take ny 1 and nx 0, then that will be maximum. This value will be greater than this value. Okay, so that's why we are taking nx equal to 1. So it is going to be 1 plus half h cut omega plus ny 0 plus half 2 h cut omega. We'll solve it. It's going to be 3 by 2 h cut omega plus 2 get cancelled. Okay, h cut omega. So it is going to be 5 by it is going to be 5 by 2 h cut omega. This is the answer. So energy of the first excited state is going to be this one, 5 by 2 h cut omega. Okay, so option D is the correct option. Option D is the correct option. Question number 3 we are going to solve. Question number 3. Question number 3 is, consider a particle in one-dimensional potential. Consider a particle in one-dimensional Consider a particle in one-dimensional potential that satisfies that satisfies that satisfies v, which is function of x equal to v, which is function of minus x. That means that it means symmetric potential. Okay. Psi psi psi1 denote the ground state, denote the ground. Okay, just wait, not like this. Let psi0 and psi1 denote the ground state and first excited state, first first excited state first excited state ground state and first excited states respectively, respectively. Let and let psi equal to alpha naught psi0 plus alpha naught alpha1 alpha1 psi1 be a normalized state, be a normalized state with alpha 0 and alpha1 being real constant, being real constants. The expectation value x of the position vector, position operator x in the state psi is x in the state psi. Options are option number A, alpha naught square psi0 plus alpha1 square psi1 x psi1. Option B is alpha naught alpha 1 psi 0 psi 0 x psi 1 psi 0 x psi 1 plus psi 1 x psi 0. Option C is alpha naught square alpha 1 square, and option D is 2 alpha naught alpha 1. Okay, so this is the question. Consider a particle. So there is a particle which is in one dimensional potential that satisfies Vx equal to V minus x, right? So it's a symmetric potential is given. Let psi 0 psi 1 denote the ground state and first excited state respectively, and let psi equal to alpha naught psi naught plus alpha 1 psi 1 be normalized state with alpha 1 alpha 2 alpha naught alpha 1 being real constant. The expectation value of the position operator x in the state psi is given by, so we need to find out expectation value of position operator. Okay, so very easy question. So since that is Vx equal to minus Vx, right, that is potential is symmetric, and potential is symmetric. Okay, potential is symmetric. So in this case what happens is psi 0 x psi 1, this value psi 0 x psi 0 is going to be 0, this value, because potential is symmetric, so this value is going to be 0, and similarly psi 1 x psi 1, it is also going to be 0. Okay, so now we'll and psi is normalized function, right? So expectation value of x is going to be psi cat is given, so bra is also going to be the same because there is no iota present, right? So we'll just put the value, so it is going to be alpha naught psi psi naught plus alpha 1 psi psi 1 x into alpha naught psi naught plus alpha 1 psi 1. Okay, so we will solve this, and so this is going to be, since alpha naught x psi naught x psi naught and psi 1 x psi 1 is 0, so it is going to be, we will simplify it further. So it is going to be alpha naught alpha 1 into psi naught x psi 1 plus psi 1 x psi naught. So this is the correct option answer. Okay, so this is the question number 3rd. Now we are solving question number 4th. It's a very good question actually. Okay, we'll solve this in next page. Question number 4. The perturbation h dash equal to bx to the power 4, where where b is constant, b is a constant, b is a constant, is added to the one dimensional one dimensional harmonic oscillator one-dimensional harmonic oscillator potential Vx equal to, which is V which function of x, equal to half m omega square x square. Which of the following denotes the following denotes the correction to the ground state energy, correction to the first order in B, to first order in B. Okay, and hint is given as well. The normalized ground state wave function of one dimensional harmonic oscillator. So ground state of one dimensional this is given in this question, but sometimes it is not, sometimes you may not get this, right? Sometimes they, let me just check. So also memorize this, okay, this ground state function. So it is phi 0 m omega upon pi h cut to the power 1 by 2 into e to the power minus m omega x square upon 2 h cut Okay, so this also, there is a for simplifying this question, integration is also be given. Okay, so integration minus infinity to plus infinity, uh, x to the power 2n e to the power minus x square. Okay, e to the power minus ax square equal to e to the power minus n minus half gamma n plus half. Okay, so this is given, and options are, I will write option in next page. Options are 3b h cut square, 3b h cut square upon 4m square omega square, 4m square omega square. Option B is option B is 3b h cut square, 3b h cut square upon 2m square omega square, 2m square omega square. Option C is 3b h cut square, 3b h cut square upon 2 pi m square omega square, 2 pi m square omega square. And option D is 15b h cut square, 15b h cut square 4m square omega square, 4m square omega square. Okay, this is the question. Now we are going to solve it. Okay, so the question is, the perturbation is given as dash equal to b x to the power 4, where b is a constant, is added to the one-dimensional harmonic oscillator potential Vx equal to half m omega square x square. Which of the following denotes the correction to the ground state energy to first order in B? Okay, so we know the wave function. Okay, so and perturbation is given, and the wave function which is given, this is normalized wave function. Okay, so we'll directly find out the correction into ground state energy to the first order in B. Okay, so E10 is going to be 50 dash 50. Okay, because it's normalized function. So it is going to be infinity is going to be m omega upon pi h cut to the power 1 by 2. It will become, because it will get multiply, and b, and it's going to be x to the power 4 e to the power minus m omega square, m omega x square upon h cut. Okay, because we have put a brass I naught and cat I naught value and multiplied, so that's why we got this value dx. Okay, okay, so now it is going to be minus infinity to plus infinity. So we'll take it outside. It is going to be m omega upon pi h cut whole to the power 1 by 2 b, we take outside, and this is going to be integration minus infinity minus infinity to plus infinity. Okay, it is going to be x to the power 4, so we can write it x to the power 2 power x to the power 2 into 2, we can write it x power 2 into 2, and this is going to be to the power minus m omega h cut, we'll take it as a x square dx, right? So we'll use this hint which is given, that is minus integration, that is minus infinity to plus infinity x to the power 2n into e to the power minus x square equal to a minus 2 minus half gamma n plus half, right? We'll use this formula here in this one. So then it is going to be, here n is 2. Okay, so it is going to be correction to the ground state energy to first order energy is going to be, this is going to be, after applying this hint, it is going to be b m omega upon pi h cut to the power half. Okay, so what is a here? A is m omega upon h cut, m omega upon h cut to the power minus 2 minus half, right? Like it is given in hint, this one. A is here m omega upon h cut. Okay, and this is going to be gamma n is 2. After solving, it is going to be 3 by 4 b h cut square upon m square omega square. Okay, so this is the answer. Which option is matching? We'll check it. So option A is matching. Okay, so option A is the correct option. 3b h cut square upon 4 m square omega square. 3b h cut square upon 4. Okay, this is the correct answer. Okay, so guys, thank you so much for watching my video. Okay, so I'm going to stop here, and I would request you guys, my courses are absolutely free of charges, so you can watch at any time. And those who have not subscribed my channel, please subscribe my channel and watch free lectures, and these lectures are actually to crack your examination related to physics. Okay, okay guys, thank you so much. Good night.